So let me explain what's the meaning of this linear first order ODEs. Yeah. First, we know to solve ODE, most of the ODEs we cannot solve. Yeah. In the real world applications, most of the ODEs we cannot find nice formulas for the solution. Yeah. But later you will see, you will learn, if we cannot find nice formulas for ODE, then we have a chance we use computer. Yeah. So right now, because we can write program, we try to find approximate solution. Yeah. So that means if we cannot find, because most of the time we cannot find formulas. Yeah. Formulas. Yeah. Then we have the second method. We will use numerical approximation. Yeah. We can calculate numerical solution. Yeah. Approximate the real solution. Very close to the real solution. Yeah. All right. Yeah. But here we try to do more. We try to explore more different types of ODEs that we can use formulas to solve. Yeah. Here, we consider first order. Yeah. Our module 1 first order. Yeah. So module 2 second order and higher order. Yeah. Second order, then higher order. Yeah. Yeah. All right. So first order. Yeah. Although first order it looks simple, but we can only solve some special type of first order. Now, for arbitrary first order, most of the time we cannot solve. Okay? So we can only solve some special types of first order ODE. So this is one special type. Yeah. Y prime plus coefficient, a function P of X. Yeah. So here you have, any P function, yeah, here. Yeah, actually, when we say any function, usually we mean a function should be good enough. Yeah, good enough. Yeah, yeah. Because later we will take integral. We will take integral on this P function. Okay. Yeah. So we want to have a P function such that its integral is available. You can find it. It's integral. Yeah. If its integral does not exist, then this function is too bad. Yeah. So we assume its integral exists. Yeah. Then R function. Yeah. Quite general. Yeah. But if first order ODE has this structure, then we have some special method we can find a solution. Yeah. The special method, that's just we learned last time. Remember last time? Extended exact ODEs. That method. Extended exact ODEs. Yeah. So we use that method to solve. All right. Yeah. Before we solve this ODE, let's look at the concept linear ODEs. What do you mean linear ODEs? Right? So here, I want to clearly describe why we call it linear ODEs. All right. Yeah. So the reason we call it linear ODE, yeah, we look at the structure. Yeah. All right. With respect to a variable x, a linear function has the form. First, let's look at the definition of linear function. Okay. General. Yeah. Concept. If we treat x as a variable, then AB as constant, two constant. Okay, ax plus b. It's a linear form. Okay, yeah, a typical linear form. All right. Yeah. Then we apply this linear form understanding. We look at our equation. This equation. Yeah. So when we say linear, what do we mean? Yeah, the specific meaning, the meaning. Yeah. All right. First, with respect to y prime. Yeah. here. We only look at the y prime. We can ignore other terms without y prime. So we only consider terms with containing y prime symbol. It is linear. If it is linear, yeah, so then we say, yeah, that's the first requirement, okay? Not done yet. Yeah, we have second requirement. Second, with respect to y, yeah, we only look at the y terms. Yeah, okay? Other things we treat as constant, okay? We only look at y terms. So all the other terms we treat as constant, okay? All right. Then it is linear. It is linear, okay? If these two conditions are satisfied, yeah, then we say this whole equation is a linear ODE. All right. Yeah. So next, yeah, let's solve this ODE. Yeah. All right. Here, some terminology in engineering. Yeah. So, because this type of equation appears frequently. Okay. Yeah. Frequently. Yeah. So then, from the application point of view, yeah. So when this equation appears, yeah, you know, so the engineering people, they understand in another special way. So their understanding is that R function, right-hand side R function, they treat it as an input, yeah, input data, okay, input data. Yeah. Right-hand side function, input data, okay. Then this P of x, this function, that's the part of the system. Yeah. Because you have a system, okay? Yeah. Yeah. Black box, okay? Yeah. System. So then the input data enters that system. Yeah. So P of x, that's part of the system. Okay? All right. And the output, y is the output. Okay? Because you need to produce the solution. The system needs to produce the output as the solution. Y function is the solution, right? So that when the input is the R function, the output is the Y solution. Yeah. So that's the, engineering point of view. Yeah. Then, in order to solve the equation like this, there is another basic useful concept. That's the homogeneous linear ODE. This homogeneous concept. Because this homogeneous concept, when we solve ODEs, it is very useful. Because we need to do an intermediate step. This homogeneous. First, I need to explain what's the homogeneous. Okay? This original equation is not homogeneous. Okay, that original equation is not homogeneous. Yeah. Homogeneous means when the R function, when the input is 0, okay, R function is 0, then that function, right-hand side is 0, then you only have the same left-hand side of the original equation. You replace R function by 0 function. We call this is the homogeneous version of the original equation. So you may ask, why we need to consider the homogeneous version of the original equation? You will see this intermediate step is very useful. Yeah. Later, when we solve many other equations, we always need to work on solve the homogeneous version of the original equation. Yeah. Why? The reason is, you will see, the reason is because usually an ODE has many solutions, not just the one solution. An ODE usually has many solutions. When we solve an ODE, we want to find all the solutions. Okay? Yeah. Yeah. So this homogeneous version will allow you to cover all the solutions. Okay? So that's why it's important. Yeah, so we need this step. Yeah, all solutions. Yeah. All right, so let's consider this homogeneous linear ODE, the first step. Yeah. All right. Yeah, the simple way, it's a separable structure. Yeah. As a separable ODE format. Okay, then we take integral. Yeah. Yeah, we apply the standard formula, so we, so we can find the solution. Yeah. But next, we write y function as a simple function, as simple as possible. Then you can see that question: how to remove the absolute value of y? Yeah. Yeah, because in the original formula, you have the absolute value, positive, negative. But when we write the final formula, we don't want to carry that absolute value, right? To make it as simple as possible. Yeah, so that the question we need to answer, how to remove that absolute value. Yeah. Because here, it's hard to say y must be positive, right? Yeah, because you don't have information. You don't have sufficient information to say y must be positive, right? Nobody can say y must be positive, right? Yeah, but here, there is a simple way to get around the problem, positive, negative. Okay, all right. So let's write. So here I write the result, y equals that constant c. Here you can see, this formula does not have the absolute value. But you may ask me, why you can write in this way, right? Why you skip that? Why you skip that positive, negative? Yeah. Here, let me write a few intermediate steps to show you we can use this nice form as equivalent form of the solution. Yeah. All right. If I do not remove the absolute value, so I should write one step like this: y absolute value y equals e to the e star. Oh, sorry, e to the c star, right? Constant. C star, right? Yeah. Then e to the negative, that integral p dx, right? Yeah. So this intermediate step, the first one. Yeah. Then, second one, we don't want to remove absolute value sign. But when you remove it, you cannot remove it directly. All right? If you remove directly, you cannot justify it, right? You cannot justify it, yeah? Because it could be wrong, right? So we need to justify it. Yeah, all right. So here, how about this? We want to justify why we can remove absolute. First, let's assume when y is positive, we can remove, right? When y is positive, we can remove, okay? All right. So, oh, sorry. Yeah. Too bad. Yeah. All right. Too sensitive. Yeah. So when y is positive, yeah, we can remove So this is under the condition y positive. Okay? But when y is negative, what should we do? When y is negative. Right. When y is negative, we should put the negative sign, right? put the negative sign, right? Yeah. Now you look at this part. Yeah. E to the negative C star, can we treat it as some positive constant? E to the C star, we can treat as an arbitrary positive constant, right? Yeah. Then, yeah, suppose this E to the C star, we treat it as C, okay? Yeah. Positive C. Yeah. All right. But here, negative C, right? See? Then, with this analysis, can we combine these two? When y is positive, we use positive C. When y is negative, we use negative C. All right, now we go here. Here we do not assume C positive or negative. We allow C to be both positive or negative. Can we just put a constant C here? Because it covers both positive and negative, right? It covers positive case, that case. It covers negative case for this case. Yeah. So that's why we can use the simplified way to write the final solution. Okay? Yeah. So here you can see, yeah, after a few intermediate steps, yeah, although that step is skip it, yeah, yeah, but when that happens, yeah, similar situation, so you can use let's say we can use a non-zero constant C. How about that? We only require C is non-zero. How about that? Yeah. So that C non-zero constant is determined by the initial value. If this equation has some initial value, then we use initial value to determine that C. But for the general, we don't have initial value, so we keep that C constant. Yeah. All right. Yeah. So that's this step. Yeah. All right. Homogeneous. Yeah. All right. Yeah. C determined by initial condition. All right. Then we can get to this non-homogeneous linear ODE this time. Yeah. Yeah. So we put it aside, yeah, homogeneous equation. So we put it aside. Yeah. So now we continue, yeah, to fix the R term this time. Yeah. All right. Yeah. To solve this equation, yeah, finding an integrating factor. Yeah. So that's our, extended exact ODE integrating factor determined. Yeah. All right. So let's write this original ODE as this differential form. Yeah. Because we want to use that total differential method to solve this one. So what we did last time. Yeah. Total differential form to solve. Yeah. All right. Yeah. But yeah. When we work on integrating factor, there are two different ways, right? Yeah, two different ways. Yeah. All right. Yeah. So the F integrating factor. Yeah. So the question.
We're able to write the Rx in the same group as Px.
Oh.
Kind of confused by the
All right. Yeah. Yeah. Okay. Yeah. So same group. Yeah. All right. Y prime equals dy over dx. Okay. dy over dx equals, or we write this way, plus py minus r of x, right? Equals 0. Yeah. So then you multiply dx both sides, so you get this term dy and 0. Okay? Yeah. 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 All right. So we are here. Okay? Yeah. But we need to determine that f. Okay? Yeah. When we determine f, we know there are two simple ways we can try. The first way, f is a function of x, only a function of x. But second, f is a function of y. Two possible ways. Okay? When f is a function of x, then the criteria, remember, the exactness criteria will give us, after simplification, will give us this one. Yeah. Because when f is a function of x, we will have f sub y equals 0. Okay? Yeah. If we do that, exactness criteria checking, yeah, the f sub y term is gone. Yeah. So the left-hand side will only have one term. Yeah. Similarly, the right-hand side, not right-hand side, because there is a second case. Second case, when f is a function of y, then f sub x equals 0. F sub x equals 0. All right? Yeah. So then, that term, yeah, because this term, yeah, this term, because it corresponds to f sub x equals 0. Okay? Yeah. All right. But the f sub y not equal to 0. So we need to keep that term. Yeah. So here you can see there are two cases we need to consider. Yeah. In order to choose good f function, there are two cases we need to consider. Yeah. The first question we need to answer, which of the two cases would give us easier form? Yeah, because we want to pick the easier way. Yeah. Which of the two, the first one or the second one, we will have an easier ODE to solve? Yeah. Okay. The first one, second one. All right. Yeah. Okay. Yeah. Remember Q function. This Q function is 1. Yeah. From this equation, original equation here, Q is constant 1. Q is constant 1. That means Q sub x equals 0, right? These Q sub x, these two equals 0. Yeah. Right? That means this term is gone. This term is gone, right? Yeah. Because Q is 1, right? Q is 1. Then Q derivative partial Q over partial x, 0. 0 means the last FQ sub x term is gone, right? Then these two equations, which one you feel easier? Yeah, first one easier. First one easier. Because Q is 1, right? Q is 1. Then you do, but here, P sub y, now, so you get a fraction. Yeah. All right, yeah. So the Matthews said the first one is easier. Because this one, you will get, we simplify, f prime equals p y f, okay, after simplification. The second one, f y over f, yeah, equals negative p sub y over p. Yeah. But p sub y, yeah, this is p. This is p. This whole parenthesis, this is p, capital P. P sub y, just a little p, okay? Yeah. Partial p over partial y, just this little p. Yeah. So that little p over capital P, still very complicated, right? Yeah. Because this little p over capital P, very complicated. But this one, f prime over f equals p sub y, little p. You only have little p, no denominator, right? So the first case is easier. So we should work on the first case. not the second case. All right, so we select that. Yeah, because this criteria help us get those two equations. Yeah. All right, we select the first one. Then let f equals f of x. Yeah, so we get that equation. After simplification, the q last term is gone. Okay. After simplification, we get this one, and solve, because partial capital P over partial y, that's little p, right? That's little p. Okay. All right. Then we can solve this equation easily. Yeah. df over f equals p times dx. Yeah. Natural log absolute value of capital F equals this integral of p function. We introduce a new notation, little h function, represent that. Yeah. Just we want to make the expression shorter, compact, more compact. Yeah. Concise. All right. Yeah. Then absolute value f again. So how do we deal with this absolute value f? Yeah. Here, situation. Here it's different from our previous situation about absolute value, because here we only need to find one f. We do not need to find all possible f functions, right? You only need to find one. Then you just find the simplest f. Okay? So you take the positive version. Yeah. So you remove the absolute value. You only take the positive version, e to the h. Yeah. You do not consider negative version. There is a negative version, but you want a simpler, positive version simpler. Yeah. So this is your integrating factor f. Yeah. So we complete this step. Yeah. After that, next step, we multiply the integrating factor, and this new equation becomes exact, right? Yeah. Based on our theory, after we multiply this integrating factor, because we use the exactness criteria. So this new equation should satisfy this criteria. That's why it is exact. That means we can make the left-hand side total differential, du. Left-hand side just du. So we need to find a u function. Okay? Yeah. So how to find a u function? We do two integrals. Yeah. U function. First, the integral on m function. Okay? So m function, but we need to add a constant term, has the form little k of y. Yeah. Because we treat x as variable, so everything about y we treat as constant. So little k of y. This as a special type constant here. All right? Yeah. But the m function is that one. Yeah. So m function is this one. Yeah. So if you write that, and so here. Because here we need to do some preparation. Yeah, we need to do some preparation here. Yeah. Because mx is this one, and remember p is h prime. Yeah. Look at that. P is h prime. Look at the definition of h. Why p? Look at this is the definition of h, right? Yeah. Integral of p equals h. Then you take h prime, you go back to p. Yeah. So you take h prime, you go back to p. Yeah. So that's why we can write p as h prime. Yeah. Because in that way, we'll take the integral, it will be easier. Yeah, it will be easier. If it is h prime, it will be easier. Okay? All right. So you take integral on m function, this p, yeah, you take integral here, the p h prime, you will get that, then that. So can you see that? So here, probably I need to write a little more, yeah, because here, yeah, here we want to calculate integral on that term, right? Integral h prime y minus r, yeah. But the integral, remember, with respect to x, right? With respect to x, that means we treat y as constant, right? Yeah, because when we take this integral, we treat y as constant, right? So, can you get y constant? You can take out, right? Prime minus right? Two separate integrals. Two separate integrals. All right. Yeah. But the first term, the second term, we do nothing. We keep the second term. Okay? This is the second term. But the first term, we can find its expression. The first term. The first term, yeah, let me just work on this part. H prime can you combine h prime with dx? H prime with dx, that's dh. H prime times dx equals dh. Can you see that? Yeah. All right. So that is h dh. Then it equals e to the h. Okay. E to the h. H prime, so here I use this, yeah, here I use this. H prime times dx equals dh. Differential relationship. No? Differential relationship. If you feel hard to see it, you divide it by dx, both sides. The right hand side, dh over dx equals h prime. Then you can see that, right? Because dh over dx equals h prime. Yeah, that's the way to write derivative. dh over dx, that's the derivative, h prime. Yeah. Yeah. So with that, you get the first term. Yeah, because here we only do the integral part. The y, we carry the y down. So y times e to the h. First term. Second term we copy. So we do nothing. Yeah. First term, we simplify it. Yeah. All right. Constant, you don't worry about constant. Okay? Yeah. Because this indefinite integral, second indefinite integral, it contains some constant. Yeah. So you do not miss any constant here. Okay? Because the second term contains some constant. So you don't worry about the first term, you forget the constant. No. Yeah. Don't worry. Yeah. All right, that's the first integral. But you have a second integral with respect to y integral. Yeah, here. Yeah. All right. Yeah. All right. So n function. N function just this e to the h, right? Yeah. This is much easier. Yeah, but with respect to y, yeah, e to the h, remember, h is a function only contains x, right? Yeah, so here, I want to explain why you get the first term, y times e to the h. Why is that? Yeah, because remember, h is a function, it only contains x. H does not contain y. If h only contains x, when we do the second integral with respect to y, we treat x as constant, right? We treat x as constant. Then this h, e to the h, we treat it as constant. That's why we have y times, so here, e to the h is a constant, so we have y times constant as the first integral, right? That's one. Now, so now we need to use our shortcut way. Remember last time I mentioned a shortcut way. Yeah. All right. So here, let's look at. So we write our u in these two ways, but when we need to write the final u, the shortcut way tells us you only pick the terms that appear in one of the two expressions, like a union of the terms. Yeah, let's understand. Like we take the union of all the terms, all the explicit terms. Okay. Yeah. Other than little k function, little l function. Yeah. We take a union of all the terms to write the final u function. Yeah. So this y times e to the h, because up here both sides, union will only take one. Okay, one copy. Yeah. This integral one, negative integral r e to the h, this one, because it appears in the first expression, so we copy it down. Okay? Yeah. If a term appears in one of the two expressions, we copy it. Yeah. And at the end, little l function, little k function, so we use constant c. Right-hand side constant c. Yeah, because after you cover all the terms, the last thing is constant c, right? Because our left-hand side, we cover all the terms from the two expressions. We cover all the terms from the two expressions by taking the union of all terms. Okay? Union of all terms. So we cover all the terms, all right? Remaining, after you cover all the variable terms, the remaining is the constant. So we use right-hand side, we use one constant at the right-hand side. So we get the u function. Yeah, so that's our final solution. Yeah. All right. Yeah. So that is, so we saw, so you can see after this step, this u function. Yeah, but just a minute. After this step, although this is already the solution, but you can see this solution actually is relatively easy. Relatively easy. Yeah. So we can further to write y equals a form, right? Yeah, because you only have one term contains y, right? Yeah. Y times e to the h, you can divide it by e to the h, you can get a y equals certain function of x, right? Yeah. So we can write, this means we can write a simpler version of the solution that is explicit form of the y function. Explicit form. Yeah. So the last step, we write the explicit. Yeah. So I copy and yeah. So the last step. Yeah. You couldn't see. So let me erase this. The last step. You couldn't see. Yeah. Last step. Okay. Because we can write y explicitly. Yeah. You move the term divided by e to the h, so you get an e to the negative h, and h, based on our definition, that is the final solution. Okay. That is the final solution. Yeah? Okay? Yeah. Yeah. So this here, we have the general formula of the final solution. Yeah. Okay? Yeah. All right. Then, yeah. So later you can see, so any first order equation with this specific form, you have a formula to write a solution out. Okay? Yeah. So you just match the pattern. Match this pattern, then you can apply that formula. Yeah. All right. Yeah. Next, solve linear first ODE by formulas. Just one simple example. Yeah. So let's apply. Yeah. So for the concrete example, yeah. But this time we apply the formula to find a solution. Yeah. Straightforward. Yeah. From this equation, you know P function and R function, right? Yeah. So you compare with our standard form, the P function and R function. Okay. Yeah. But you have an initial value, so you can determine that C constant using this initial condition. All right. Solution. Yeah. Formula to be used. Yeah. Yeah. So we go back to the general form of the first order ODE. So this one, yeah, but we have the specific P function, R function. Yeah. Solution, we plug in, right? Yeah. When we plug in, we calculate H function first. Yeah. In the formula, we need to calculate H function first. Yeah. Because Y has the form, but the H integral of P function. Yeah. All right. So let's calculate the H function first. The integral of tangent X function. Yeah. Tangent, we know it is sine over cosine, right? Tangent of X equals sine X over cosine X. Yeah. All right. So then, can you write in this form? Yeah. Because sine of X. Yeah. So here I did one jump. Yeah. Because we know tangent X equals sine of X over cosine of X. Okay? Yeah. But the cosine X equals negative sine X times dx, right? Yeah. Because the derivative of cosine X is negative sine X. Okay? Derivative of cosine is negative sine X. Yeah. So that's why we have this negative sign here. Negative sign here. Okay? Yeah. So d cosine of X over cosine of X. Yeah. Then we can write H as a negative natural log of absolute value of cosine X. H function. Yeah. Absolute value. Yeah. So here we have absolute value. Yeah. All right. Yeah. Negative. We know cosine of X equals reciprocal of the secant X, right? Secant. Reciprocal. Yeah. So the negative. Yeah. So we can make it reciprocal of cosine. Yeah. So absolute value of secant of X. Yeah. Yeah. All right. Yeah. Then let's write Y. Y. All right. Y. So we plug in. Yeah. All right. E to the negative H. Yeah. So here. The reason, so H has two forms. We just pick which one is easier. Yeah, we have two possible forms we can choose. Which one is easier, then we pick the easier one. All right? Yeah. But when we calculate e to the negative h, then we want to pick the negative version. Okay? Negative. Yeah? Because negative cancel out. Okay? Yeah. So when we calculate e to the negative h, we pick the negative version. Okay? Yeah. So we get e to the positive natural log of absolute value of cosine x. Yeah. All right. So then R function times e to the h, but this time we use the positive version. Okay. No negative sign. We use positive version. Okay. So natural log of absolute value of secant of x. Then c star times, this time we use the negative version. Okay? Negative version. Yeah? So two versions. So we just pick one more friendly. Okay? We pick a more friendly version. Yeah. All right. So that's why we like. Then next, for the simplification, do you know there is a formula? There is a formula. E to the natural log of x equals x. Do you know this formula? E to the natural log of something, yeah? Because the exponent base and the log base cancel out. So you only keep the x, right? So that's why, so here, the first term, e to the natural log of absolute value cosine, you only keep the cosine x. Okay? Log, exponential, yeah, because they're reverse each other, right? So cancel out. Yeah. So that formula, so you simplify it, you get a absolute value of cosine. So you still need to keep the absolute value. Yeah. Because be careful, don't throw away. Right? Absolute value. Then absolute value of secant of x, then plus c star times absolute value of cosine x. Yeah. Next, because eventually we need to remove absolute value sign. Yeah. But before we get to the last step, so we should carefully keep all the absolute value sign. Yeah. And we need to do some analysis before you can remove the absolute value sign. You need to do some analysis. Make sure you're okay. Yeah. So you do not mess up. Okay? You do not mess up. Yeah. All right. So let's continue. Yeah. All right. Yeah. Two cases. Yeah. Absolute value. Yeah. Cosine of x greater than 0, cosine of x less than 0. We have two cases. So we want to write the formula in two versions. Yeah. Positive version, negative version. Yeah. All right. The positive version, yeah, when cosine of x greater or equal to 0. Yeah. If we assume cosine of x greater than, so then can you, yeah, so here, yeah, here some students may argue, so if it is rigorous, yeah, so here we assume in this way, in certain interval, yeah, because cosine of x greater or equal to 0, in certain interval, okay, yeah, because when you take integral, you need to consider certain integral, right? Yeah, so here we assume in certain interval we have this cosine of x greater or equal to 0. Yeah, so we so the second one, yeah, but some of you may worry about the first term. Yeah, first term because, yeah, positive, yeah, so positive because cosine is positive, so you can remove absolute value sign directly, right? Yeah. Remove absolute value sign directly. Okay, so then after simplification, so you get that expression. Then when cosine of x less than 0 in certain interval, this time when you remove absolute value, you need to write a negative sign here. Yeah. But the first term, negative cosine, you have two negative cosine, negative, positive. Yeah. Because this secant, you have another cosine. Secant, you have a negative cosine. Then the first, you have a negative cosine. Cancel out. So it's positive. So the first term positive, but the second term is negative. Yeah. Now the last step, we want to remove these two versions. We want to combine these two versions. All right. How about these two versions? Yeah. Because cosine of x is positive, can we treat as plus c star absolute value of cosine. Okay? Can we treat this second, because minus, can we treat it as plus C star cosine of x? Yeah. Because, yeah. So in this way, so you have that, you combine these two forms. Yeah. So the second one, so you go back to the cosine. Yeah. You still have one absolute value, but it's okay. Yeah. All right. So this one, actually, when you write one version, you have absolute value sign. Yeah. Okay? Yeah. But when you need to determine that C, with that absolute value sign, you can determine C, right? Yeah, absolute value, you can determine that C. So you plug in x equals 0 to determine that C. Plug in 0, okay? So y of 0 equals 1. 1 equals C minus 2, so C equals 3. Yeah. C equals 3. Yeah. C equals 3. Yeah. And here, your initial value, so here, your initial value is in the interval cosine of x greater than 0. Yeah. Is in some interval, that interval. Yeah. All right. So then your final solution C, yeah, at some 0 containing the 0 point, you have C, you have 3 cosine of x minus 2 cosine square x. Yeah. In some interval containing 0. Yeah. Because when you get a negative interval for cosine x, then your solution will be different. The form will be different, right? Yeah. 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 Matthew?
So what exactly are we distinguishing with the star, C star?
Yeah. All right. C star, yeah. Distinguishing. Yeah. The question. Sometimes we use C star, sometimes we use C, so you treat this way. In our intermediate representation, we need to use constant, right? So our intermediate representation, when we use constant, it's not the final constant. We use C star. Then the final version of the constant, we use C. Yeah.
So C star is like, it could be positive, it could be negative.
Yes. Yeah. Yes. Yeah. Temporary. The reason we don't want to, because this C star and our final C could be different, because we can change. So we don't want to confuse. Okay. So C star, if you use C here and then later another C, but these two copies of C, they could be different. Then we get messed up, right? So that's why people intentionally put a star. So because this constant is different from our final constant. So you separate. Yeah. So you will not mess up. Yeah. All right, so let's take a 10-minute break. Yeah, so we'll come back. So let's do the